Hi everyone, welcome to today's practical. Today we're looking at alternative A, Waec 2023 specimen, and we are looking at the first instruction. The instruction was asked to provide a helical spring, or you can see use a spiral spring for the experiment. We also asked to provide some masses. We also asked to provide meter rule and knife edge. So this, and of course we're going to ask to provide our stopwatch. So this experiment could be based on oscillation and also be based on principles of moment. But for today, we're going to look at the oscillation part of it. So the number one question, as a Waec student, you expect to have question on simple harmonic motion, oscillation, or you can still have a question coming from moment based on the instruction provided. So the question, we're going to first measure the length of the helical spring. The length of the spring is, the one I have here is 7.50 cm. Then I have a mass hanger. The mass hanger for hanging the weight. The mass hanger here is 50.00 grams. So we now go to the experiment proper. This is the mass hanger. This is the spring hanging there. This is the mass hanger there. Then we're already got the length of the spring, which is LO, the unstretched length of the spring. Then we are told to slot in the first mass, which is 20.00 grams on the mass hanger. So we'll slot in the first mass, and then when you slot in the mass, there's going to be an extension. We now find the new length. Measure the spring. The new length is around 12.00. So that's the length when a mass of 20 grams is hanging on it. Then we have to find the extension for the equation. The extension is the difference between the new length and the original length. That is 12 minus 7.5. And that will give you 4.500. The next thing is we're going to set this mass into 20 vertical oscillations. So we are ready to start. We displaced it slightly, and then I will now progress to count. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So what the time? We have 18.78 seconds. 18.78 seconds. So I repeat the experiment again for 20 conversation and then take the average time. So I remember to repeat it. Okay. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have 19.85 seconds. So we'll add the two and find the average of the time. You can do it 3 times, but why we do it 1 or 2 times is for us to avoid error or minimize error in the experiment. So add the 2 and divide by 2. divided by 2.
19.32.
So we have about 19.32 seconds. Divided by 20. We also have the period of oscillation. As 0.966 to 4SL. Multiply by 960 times 0.960. .9332. So this is what we have when we oscillated 20 gram mass. Now the next we're going to use a 40 gram mass. So already we have 20 gram here. We now slot in an extra 20 gram. Give us 40 gram mass. Before the oscillation, we have to find the length of the spring. How to say the spring? And find the new length of the spring using the centimeter end of the rule. So 13.5. So 13.50. The extension will be 13.5 minus the original length. That gives us 6.000 to 4SL. Okay, having done that, we now subject this mass to 20 vertical oscillation. Are you ready? Your stopwatch. One, two, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We have 21.02 seconds. Repeat. When you repeat the experiment and take the average time, withdraw slightly. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have 22.03 seconds. Add and divide the two. 21.02 plus 22.03. Divided by 2. I have 21.53 seconds. So divide this value by 20, please, to find the period of oscillation. 1.077. Square this. 1.1599. Okay, 1.160. Okay, we'll now go to the 60 gram mass. So we already have 40 here. We'll now slot in under 20, making it 60 grams. We'll now take our new length of the spring, or the extension, of course. New length of the spring. This is 15. Yeah, 15 cm. 15.00 centimeter. So the extension is the new length minus the original length. So when we subtract this, we also have the same 7.500. That is it. Then we now move to the oscillation. Ready? Stopwatch to 0. We display slightly. No, it's not gyrating. I have to repeat it. Alright. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. No, that is wrong. I have to redo it and then repeat it because of the interference of this rotor stand. Hold on. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have about 24.59 seconds. Okay. We're going to do the experiment again and then see the average value. Okay. 1, 2, welcome. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, no, that fresh. 1, 2, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So this gives us 24.64 seconds. So please let us have the average of the value. 24.59 plus 24.64. 24.59 plus 24.64 divided by 2. 24.62. So divide 24.62 by 20 give us the trigger oscillation. 1.231. Here this is 1.515. 1.515. So now move to the fourth stage, 80 gram mass. Already here we have 60 grams. We slot in under 20, giving us 80 grams. Now we take the length of the spring using the centimeter end of the rule. And we are getting about 16 centimeters. So 16.00. Then the difference between this length and the original length is my extension. That gives us to subtract. That gives us 8.500. That is right. Then we now move into oscillation of the 80-gram mass. Are you ready? Move to 0, your time stopwatch. So I'll move. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, that is wrong. It should be repeated. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I have 28.32 time here. So do the score 1. Return your time to 0. With 8.32. So repeat the score 1. Then return your time to 0. About to start. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and then 20. Now 27.34. So please help me find the average of this time. So with the limit experimental error, the average will be more accurate. Divided by 2. $27.83. So divide this by 20 oscillations. 1.392. Square this value to have t squared. One point what?
938.
938. So move to 100-gram mass. So come back. Remove this is 80 here, 20 each mass. Move the masses. And then we can place this 80 grams with a single 100-gram mass. Before it was late, we find the length of the spring, the new length of the spring in centimeter. That gives me 16.4 centimeters. Let me repeat to be sure there's no mistake on it. .5 centimeters. So now 16.5 cm, extension 16.5 minus this, and 7.5 gives us 9.00. Then we move to the oscillation. 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and then 20. Follow up. So 7.02. Then I'm going to repeat it again. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 26.72. So please find the average of this. The 7.02 plus the 6.02 plus the 7.02 plus 26.72. Divided by 2. 6.72 divided by 2. 6.96, yeah, divided by 20. 96 divided by 20.
1.348.
What?
1.348.
348. Spare this value?
1.817.
1.817. Okay, let's look at that reading. We have to look at this reading and verify the experiment. We see that the time is increasing. 19, 21, 24, 27, 26. The error somewhere here because the time for 80 grams should be less than that for what? For 100 grams. So the error in this experiment. So what it means, we're going to repeat this 80 gram experiment again. We're going to repeat the oscillation because the time shouldn't be higher than that of 100 grams. So we move back to the experiment and then go back the 80 gram. This is 20, that 20, 40, that 20, 60, that 20, 80. So are we ready? Because the error could be from 80 grams or from 100 grams. So I'm going to repeat the 80 gram first again. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have about 25.49. So you see, this is 25 point, the error in this experiment. 25.49. We have here, I'll have to clean it up. And then do the small one and see what will happen. So the small one, let's stop it from generating. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So here we have approximately 26.06. 26 points. Okay. 0.60. So we'll add and find the average of the time. Please let me do that. Add and divide by 2. So 5.49 plus 26.60 divided by 2. We have 26.05. So we have a reasonable answer now. Value less than this. Then divide by 20 to find the period.
One point 303.
1.3 what?
303.
1.303. Then you square this value.
One point 1.700.
No, that should be that. 1.698. Still okay. So this is the value we generated. You're still on to youtube.com at Best Science Brain. So YouTube address, you can Google us and have more videos on this. Then our number remains 234-8065-985644. youtube.com / Best Science Brain 234 plus 234-8065-985644. So this number you give up if you need our services, you need private tutorial or tutorial in school or in group tutorial, will be readily available if all things are made right. So now we're going to plot a graph. We're going to plot two graphs for relationship. We're going to plot a graph of extension against t squared. We're also going to plot that graph of mass against t squared against mass. We'll have the relationship and then evaluate how it goes. Extension against t squared and then square of period against mass. Okay, so keep on watching as we go to the graph. So as you can see, this is a graph of E extension against the square of the period. The extension values range from 4.5 to 9 to 9. While the square of the period for experiment range from 0.9332 to 1.87. Then for the extension on the vertical axis, I have to choose a scale using 4 cm or 2 boxes represent 2 cm or 2 units. That is 4 cm to 2 units. This 2, 4, 6, 8, 10. Now to know what one line stands for, in the 2 boxes there are 10 lines for each box, 10 lines for each box. There are 20 lines. To know what one of these tiny lines stands for, divide these 2 by 20 as I did it here. One line is 2 over 20, 0.1. That means if here is 0, each line is 0.1, 0.2, 0.3, 0.4. You can't here is will now give you one whole number. Until from there you can read your scale very well. Then for this other axis, the values of t squared are small values from 0.9 to 1.87. We'll give 0.2 unit. 1 cm to 0.2, 2 cm to 0.2 unit. That is one box to 0.2 unit. So 0.2, 0.4, 0.6, 0.8, 1.0 up to 1.8, which is the last value we have. So to know what one line stands for, we divide 0.2 here with 10 lines as I did it here. For t squared axis, one line is 0.2 divided by 10. We now have 0.02. So one line here is 0.02. From there, you can read your values, and then we plotted. When we plotted, we have about 3 points in the line and 2 close to the line. So we have to draw our best line and then took our slope. The slope is the change on E axis. Change on E axis, which here will be our E2. The value here will be our E1. Change on E axis all over the change on T squared axis. So we'll take the fair value of E, read it off here, which gave us 9. Second value of E, we move down there, we gave us 4.5. Then T squared, the fair value is 1.8. Second value is 0.93. So we now solve out 9 minus 4.5 give 4.5. 1.8 minus 0.93 will give us 0.87. The unit is cm, while this one is second squared. We want to work in standard unit. We convert the cm to meter, divide 4.5 by 100. We now have 0.045 meter. While this one is written in second. When we divide, we have our slope as 0.0517 meter per second squared from our slope from this experiment. So next, we're going to the next graph. You can get from this relationship. The next graph will be the graph of T squared, square of period versus mass. In case we are out to find the intercept, you can still find your intercept on the horizontal axis. In this graph, the intercept on the horizontal axis is, you read it, 0.02, 0.04, 0.06. So the intercept on the horizontal axis, which I can call C, is now 0.06 seconds squared. That's the intercept, but the graph did not hit 0 on the horizontal axis. So stay tuned as we go to the other graph of T squared versus mass. Okay, here we have the graph of T squared against mass. The T squared values here, this one graph, and then mass on this side. The relationship we're getting from the same experiment. The first graph we had was E, that of E against T squared. But this time we plotted T squared against mass. So the T squared values range from 0.933 to 1.817. So our scale will have 0.2, 0.4, that means 0.2 unit to 2 cm or to 1 bus, 0.2, 0.4, 0.6, 0.8 up to 2.0, 1.8, then 2.0 over there. The least value, the higher value is 1.817. Then the mass, the values of the masses we have 20, 40, 60, 80. So we have 20, 40, 60, 80, 100. This one is simple. We use 2 cm or 1 bus to 20 units on the mass axis. Then before you start plotting, you have to know what one line represents in each of the axes. For this one line, one tiny line here will be 0.2 divided by 10 lines, which we did over there. So one line there is 0.02. Why? For this one is very simple to understand. For this one line here will be 20 divided by 10 lines, which we did here to get 2 units. So but this one is very simple, but the other side we are going to read it. Then after plotting, we have 5 points on the graph, and then it happened that we have 3 points falling in and then 2 points off. So we have to take the best line, 3 points. Then we have to take our slope, which is the change on the vertical axis, that the change on the T square axis, all about the change or the difference on the M axis. We put the value of T squared there, which is around 1.8, minus the value here, which is 0.93. The value of the mass here, 100, minus the value there, which is 20. Solving this out, we have 0.87 seconds square with the unit of t squared all over 80 gram. So we have to convert this gram to kilogram. That's our unit. Then we divide. After dividing, we have the value 10.88 seconds squared per kilogram. Yeah. Then that is the slope of this experiment. Then the intercept. The intercept, we have to find the intercept. Now the intercept in this graph is on the vertical axis. The other one would be the intercept. That is it. The first one, the intercept was on the horizontal axis. That is the graph of E against T squared. We got the intercept on the horizontal, we got it as 0.06 seconds squared. So for this one, the intercept is on the vertical axis. Reading the intercept, we have 0.70. And then the vertical axis is second, also second squared. So you look at the two values, okay, now, can continue, 0.70 seconds squared. Then assume we are asked to find this expression. Sometimes they give an expression to evaluate k equal to 4 pi squared over s, where s is the slope of the graph. We'll now use pi value. If you're giving pi as 3.14, use it. They give pi as 22 over 7, use 22 over 7 in place of pi. Whatever they give you on the paper, you use it in place as your pi. You substitute pi with this value square all over the slope, and then evaluate this. We'll have 3.62 kilogram per second squared. Because the unit of the course, we know that pi is dimensionless, so there's no unit for the numerator, while the denominator has unit of seconds squared per kilogram. So when you invert the unit of the slope, second square coming up becomes per second square, then per kilogram coming up becomes kilogram. So this is now the value of k. So some may ask you in this experiment, what precautions did you take while doing the experiment? There are two precautions. Say two precautions you took while performing this experiment. What are the precautions? You say, I ensure. You don't say go and do this. I ensure, or I make sure, because you did the experiment. I ensure that I displace the spring through a small amplitude to avoid gyration. So you don't have to draw the spring so much so it will fall off. So you have to displace the spring through a small amplitude to avoid gyration or the spring not falling off from the rotor stand. Then I ensured that I avoided error due to parallels while reading the stopwatch and meter rule. So these are some of the precautions you have to keep in place when you are performing the experiment. There's some other precautions also, but these are also involved in this experiment. You have to make sure that the things you do. Of course, you'll be asked to state at least 2 precautions in the experiment, so which you have to do. Then I have a question here which we can look at that says state whose law. Whose law says that provided the elastic limit is not exceeded, the applied force is directly proportional to the extension produced. That is Hooke's law. F equal to KE. So you also expect them to, they ask you to state, define Young modulus. Young modulus, the ratio of tensile stress to tensile strength. Define your modulus. Define strain. Strain is the ratio of extension to original length of the elastic material. Define stress. Stress is the ratio of force applied to the elastic material to the cross-sectional area. They have a question here that says a spring is compressed by 0.03 meter. A spring is compressed by 0.03 meter. So that compression also stands, in other words, for extension, but in the opposite sense of extension. Calculate the energy stored in the spring if the force constant is 300 Newton per meter. If the force constant, the K is called the constant, or you can call the stiffness, this K, or stiffness, or you can call it force constant. So is 300 Newton per meter. You ask find the energy stored in the spring. Energy stored in the elastic material given by the formula half K E squared. You can see the formula half Fe to find the energy stored in that material. But in this situation, now we're going to apply this based on the parameter given to us. Now say energy equal to half times 300 times 0.03 all squared. So when we calculate this, we're going to have 0.03 squared times 300 divided by 2. Divided by 2, we now have the answers. I'll go again. 0.03 squared times 300 divided by 2, that is 150. What's wrong with this? 150 times 0.03 all squared. We have this as our answer. We have 0.135 joules, or in standard form 1.35 times 10 to the power minus 1 joules are the energy stored in this spring based on the equation given to us. So thank you for listening, and keep, as we're going to roll out the alternative, because as I said in the specimens in the first instruction, you expect to answer a question from oscillation from a spring or principles of a moment. So we still roll out the video for that of moment. Thank you.